Welcome back to our video module on quantum mechanics. In our previous video, we took a look at an initial value problem where we were told how the wave function started off and we had to identify what the development of it was over time. And we used a time-independent Schrodinger equation to basically develop a sum of stationary states to explain the wave over time. But I want to add some clarity to this because it's easy to miss the subtleties. For instance, one of the things that falls out from this approach is the probability of the wave being in any particular state, we'll say the nth state, is a function of the coefficient that we used over here. Basically, the probability of being in that state is Cn squared. Now for this equation, we found that if you run through the numbers, C1 is somewhere around 0.99274, which means C1 squared is 0.985, or pretty high. That means that if we look at this wave, the probability of it being in state 1 is 0.985, or 98.5%. It's really high. Well, that makes sense to us. When we looked at the original shapes of C1, C2, C3, we saw that C1 looked very much like our initial condition. So we would expect the full solution to be heavily dependent on C1. This does not mean that if we measure the wave function, that 98.5% of it is in stationary state 1. No, when you measure any wave, it chooses a stationary state. It is 100% in that stationary state. It simply means that 98.5% of the time, it'll be in state 1. And about 1 out of every 100 times, it'll be in state 3. But when the luck of the draw puts you in state 3, when you measure this wave, it is 100% in stationary state 3. Now let's look at another one of the fallouts from approaching the problem in this way, and that's looking at the expectation value of the energy, or the Hamiltonian. We see that that is the magnitude Cn squared times En. Well, what does that mean? That means that if we were to measure the energy of this state over and over and over again and find the average, this is the number we get. This is the expectation. It does not mean we'll get the average, and in fact, we probably will never get the average. What it means is that every time we measure it, we're going to get the energy corresponding to one of those states. For instance, 98.5% of the time, we'll get the energy corresponding to E1. But on about 1% of the time, like it was over here, C3, we'll get the energy corresponding to stationary state 3. So in summary, it's not like when you measure, you'll come up with the total average or the expectation value any one time, because you won't. Rather, the wave chooses one of those states and it takes on the energy of that state when you measure. Or the way I like to envision it is we imagine there's some state, some wave state as a function of position and time, and it's basically composed of 3 stationary states. And of course there's more, right? N goes to infinity. But it's composed of 3 stationary states of varying probability. When I decide to measure, when I decide to look at this wave function, it's going to choose one of these states. It might choose state 1, it might choose state 3, might choose state 2, but when you look at it, it will always be one of these choices. It will never be a combination of them. But over time, if you're to look at the average of how things work out, we are looking at a combination of the states. I hope this additional clarification gives you a better understanding of how superposition states function and how to think of wave equations as sums of stationary states. Thank you, and I look forward to exploring more potential profiles with you in our next videos.